Hey guys, today we're going to look at the last formula to calculate a confidence interval for two means. So you've already looked at one proportion, we've looked at a confidence interval for two proportions, we've looked at a confidence interval for a single mean, and now you're going to look at a confidence interval for two means, which means we're not going to have one data set this time, but we're going to have two data sets. So two different outputs of data where we could talk about I'm comparing my test grades for math, and then I'm also comparing my test grades for science. So I've got two contexts, which is going to give me a new formula. Okay, so here's the formula for a 95% confidence interval. So you're subtracting the two sample means. You have a context A and a context B. And just like the two proportions, context A and context B are determined by all the info that's provided to you in the paragraph in a question. You're subtracting the two means, plus or minus 2. Remember that 2 comes from the 95% in the empirical rule. So the 2 comes from the empirical rule, followed by the square root of the standard deviation squared over the sample size of context A, plus the standard deviation of context B squared over the sample size of context B. So it looks a little bit different from the formula for one mean, because one mean just had the standard deviation divided by the sample size in the square root. So standard deviation divided by the square root of the sample size. But here we've got a square root over everything. So it actually looks more like the two proportions formula that we know. Another thing that could be messed up is sometimes people forget this squared. So we square the standard deviations for both of our contexts. So don't ever forget to do that when you're calculating your 95% confidence interval. So one of the difficult things that you're going to have to do on a test is you're going to have to be able to determine when to use which confidence interval. So you should know that now a number out of a number is a proportion. And if I present you with two of those, then that's two proportions. Now you'll also see on average somebody did this. But if I look at how these questions are going to be set up, there's different ways that I can give them to you. I can give them to you using raw data. And for raw data, that means I'm going to have a list of numbers. But not just one list, because I'm doing two means. So I'll have one for context A and one for context B. So that's going to be raw data. I could also have stats, which means I'm going to actually give you the mean, the standard deviation, and the sample size for both context A and context B. And how the questions will be worded is I could say, on average, how many fewer points do teams give up at home than on the road? So here you have context A, and here you have context B. I could also say, if my pen will stop acting up, how many more strikeouts do pitchers get during day games compared to night games? So again, there's two different contexts that you're dealing with, and those two contexts can be presented as raw data or as stats. Okay, this leads us to our first example. So many people believe that the NBA was more focused on offense in the 1980s and more focused on defense in the 1990s. How much greater was the true mean score in the 1980s compared to the 1990s for NBA teams? So what it's asking here is it wants to know is how many more points were scored in the 80s versus the 90s. So here I gave you the summary stats of 1985 and 1990. So 1985 is your 80s and 1995 is your 90s. And we want to see how much greater the true mean to score in the 80s was. So that makes this part, the 80s, context A, and that makes the 90s context B. Now again, we talked about with two proportions that you can do it the other way around, but then you're probably going to get a more negative answer. So you just need to make sure that you know how to compare and how to discuss what that confidence interval actually means if you choose to make the 90s context B versus the 80s. Okay, so here it's a lot easier if I give you the stats because everything is already just ready to be plugged in. So that means that 110.8 is your mean for context A. Your standard deviation is 4.45 for context A, and your sample size is 23. For context B, we have 101.4 as our mean. Our standard deviation is 5.03, and our sample size is 27. So the sample sizes don't necessarily have to be the same. in this case. So then all I have to do is just plug in and calculate. So the mean of sample or context A is 110.8 minus context B's mean, 101.4, plus or minus 2 times the square root of standard deviation of A, 4.45, squared over 23, plus the standard deviation of context B, which is 5.03, over 27. And again, if you know that you're adding these two together, then it doesn't necessarily matter where you put each one of these. But if you rearrange the 110.8 and the 101.4, then that's where your confidence interval could get kind of messed up. So the margin of error does not change depending on which one you put as context A or B. But the single value estimate does change. Okay, so from here, I'm going to go ahead and just subtract. So I'll get 9.4. So that's what I think is the true mean or difference in means between the 80s and the 90s. So I think that they score 9.4 more points in the 80s than they did the 90s. If I had it the other way around, I would have gotten a negative number. So that means I believe that they score 9.4 points less in the 90s. Okay, plus or minus 2 times the square root. And you want to put everything in your calculator all at once, but I like to do everything underneath the square root first. So I put everything under here in my calculator. And how I did it is I used a lot of parentheses. So make sure that you check that you're doing this. If you're rounding as you're going, which is probably what a lot of you guys are doing, especially if you're like using a phone or something, then you're probably going to mess up a little bit and have a little bit off on the decimal place. But just make sure, like, keep 5 decimals as you're working through this for each step. So keep 5 decimals when you square 4.45. Keep 5 decimals when you divide by 23, and so on. So from here, I got 1.798. So make sure you're going along with me and checking those answers to see if you're getting something similar. Okay, from there, I took the square root of 1.78, 1.3409. So see how I kept a lot of decimal places. Even though that 9 is probably not really significant, at the very end, I'm going to see a lot of rounding differences between all of our answers. And that gave me 9.4 plus or minus 2.68. Okay, and then to get your actual interval, you're going to subtract 2.68. That's going to be the lower boundary of the interval, which is 6.72. And then on the other side is 9.4 plus 2.68, which is 12.08. So my interval ranges between 6.72 and 12.08. So that means that between the 80s and the 90s, in the 80s, they scored somewhere between 6.72 and 12.08 more points than in the 90s. So for our interpret our confidence interval, we are 95% confident that the interval of plausible values from 6.72 to 12.08 contains the true difference in means in the 1980s and 1990s. And hopefully by now you're recognizing that each time I interpret the confidence interval, I word what is actually contained in the interval a little bit different. So does it contain the true mean, which would be for a single interval? And I'm just going to kind of write this to the side. It has nothing to do with this problem, but if my interpret says it contains the true mean, that is a single mean. If I say the true difference in means, that's two means. If I say the true proportion, that's a single proportion. If I say the true difference in proportion, that means I'm giving you two proportions. So that's kind of the big thing that separates all 4 of these confidence intervals that we've looked at so far. Okay, for your second example, we want to see Do the New Jersey Devils hockey team have a greater true mean to score goals at home than on the road? So that means, are they scoring more points at home? So I'm going to make this context A than on the road context B. And what I'm going to actually do is when it's written in this paragraph form, sometimes it gets kind of confusing where everything is. So I'm going to make it just like the other slide was so that you have a list of everything and it's really easy just to plug in. So we have context A, and then in red, I'll put context B. Okay. So it says in the 2009-2010 season, the Devils averaged 3.02 goals. Averaged means that's the mean, with a standard deviation of 1.65 in their 41 home games. So context A, average 3.02, standard deviation of 1.65 in their 41 home games. So we have 3.02 is my mean, standard deviation is 1.65 in 41 games. Okay, and then for my second context, that's going to be my away games. It says they averaged 2.39 goals with a standard deviation of 1.41 in their 41 road games. So that suggests that my mean for context B is 2.39, standard deviation of 1.41, and a sample size of 41. We want to calculate a 95% confidence interval for the true difference in means. So what I was talking about on the other slide when it's interpreting it, notice that when it says calculate the confidence interval, in most of our questions, it's actually going to tell you which test you're actually doing and how to word your interpretation of the confidence interval. So you have all the values that you need, you're ready to just plug into formula. So 3.02 minus 2.39 plus or minus 2 square root of 1.65 squared over 41 plus 1.41 squared over again 41. So here they have the same sample size, but that's not really significant. Okay, everything underneath the square root, I got the single value estimate is 0.63 plus or minus 2 times the square root of 0.11329. 0.63 plus or minus 2, when I took the square root, I got 0.3365, and just be safe, 89. I especially like to keep all the decimal places if my decimal places are high, because the higher decimal places at the end are more likely to cause significant values to change when you're actually on your finished confidence interval. So plus or minus 0.67. So just to reiterate what we've been talking about for all 4 of these confidence intervals, 0.63 is my single value estimate, which stands for my best guess, not the true value, but my best guess at what the true difference in means is. So I think that they score 0.63 points more at home than they do on the road. And then my margin of error is 0.67 within a margin of error 0.67. So I think they score 0.63, but it could be within 0.67 of that value. Okay, my actual interval is negative 0.04 to 1.3. Okay, that's my interval. If you get something a little bit different, or maybe you get negative 0.05, that's probably the same answer. Again, it's just likely due to the rounding that you did when you were actually working out the problem. So interpreting the value, we are 95% confident that the interval of plausible values from negative 0.04 to 1.3 contains the true difference in means. I'm actually going to highlight this because look at the similarity here. The true difference in means, which was also the same wording that I used in the problem. Okay, for this final question, does the interval provide convincing evidence that they have a greater true mean to score at home? Explain. So here we have a negative to a positive values. So no, because the interval contains 0. Zero is a very important number when we're looking at evidence.